We are now ready to begin to learn how to picture numerical or quantitative variables. We begin with how to graph one numerical variable. We can use either a histogram, a box plot, a stem and leaf plot, or a line graph. So, if we find out that the data values collected for a quantitative variable does not have to do with some kind of time or temporal component, we might be willing to use a histogram or a box plot or a stem and leaf plot depending on the size of the data. So let's take it one at a time. Let's consider a histogram to begin with. A histogram can be drawn using a frequency, the frequencies of the counts in each class, and in which case it is called a frequency histogram. We can also use a relative frequency histogram to depict the distribution of values of the continuous quantitative variable. So, in this picture, right here, we see the heights of black cherry trees. And you will see the different classes there, or the different bins, B-I-N-S. So, in general, for this histogram, it is a graph of a frequency distribution, or perhaps a relative frequency distribution, with the horizontal axis showing the different classes, and the vertical axis showing the counts or relative frequencies, with each rectangular height proportional to the frequency of numbers or relative frequency of each class. So, when we draw a histogram, what are some important properties of a histogram to bear in mind that makes it an acceptable frequency or relative frequency histogram? Let's consider this example, which shows the prices of meal options at a restaurant called Grill and Grub. And here we have the prices. We have attempted to draw a histogram. The question is, which of these histograms correctly displays the information above, or the data given? To answer that question, we need to look at a couple of things. Let's zoom in here. And zooming in, for the first option, A, you observe that this class runs from 6 to 7, and this is running from greater than 7 to 9, because you have parentheses here. But then, after 9, you see that there is a jump. There is no accounting for from above 9 to less than 14. In this case, we can say that missing space is bad. So this is not a good histogram. Option B, rather, you have 0 to 6, and then above 6 to 9, then above 9 to 14, and then above 14 to 17. This almost seems good, except for something. From 0 to 6 seems to have a greater width of about 6 compared to 6 to 9, which is about 3. So in this problem, we have, or in this option, we have uneven class width. That makes this histogram bad. Then, question C. Meal prices at what? Grill and Grub still. But this time, did you observe that we have an empty bin? An empty bin is not useful. And because we have included that, that invalidates this histogram. Not so good. The best is this. It satisfies all requirements, and it's really good. So, whenever we're looking for a good histogram, we don't want missing space, we don't want uneven class widths, we don't want empty bins too, if possible. So, with that, we proceed to how do we graph a histogram ourselves. In this example, we're told that the file Danish coffee contains data on individual coffee consumption in kilograms per 144 randomly selected Danish coffee drinkers. We are to construct a histogram for this data. So let's go and see the data in our Excel file. So here on your screen is the data on Danish file. I'm going to copy and I'm going to take it to StatCrunch. And right here in StatCrunch, I am going to click on the variable name and paste. So I have the Danish coffee, and I'm going to go over to graph, and you can see histogram right here. So I would like to graph that of Danish coffee because that is the title of that column. And in this case, I would like value above bar, and I'd like to compute just to see what happens. Good. So I have my histogram. It is ready. I would like to zoom in a little bit on it. And once I get histogram, I'm going to follow up with the next question, which is to briefly comment on, in particular, the shape of the histogram. From the shape I see here, I can see that this is a little bit kind of bell-shaped. There seems to be a data value that is very much way above every other one. So that might suggest maybe the presence of outliers, but that is all subjective. And I can see, for the most part, this is bell or approximately symmetric. And to continue with what we have, we will need to learn what things to look for whenever we look at a histogram. What are aspects of the histogram that we should discuss anytime we have drawn a histogram like we have just done? That takes us to the next page. The very first thing to look for is the presence of bumps and valleys or gaps. Then what I want to teach you next is how to comment on these bumps or valleys. See, in this case, we have monthly average price. And I can see a bump here, the bump usually shows the most often experienced data values in the data set for which you have drawn the histogram. In this case, there is only one peak. So this is called one peak in English. In statistics, we call it uni. Uni means one, and that peak is called modal. So this is a unimodal distribution to sound fancy, statistically speaking. We have two peaks here. So 2 will be bi and peaks will be modal. So this is a bimodal distribution. Whereas this appears not to be having significantly evident peaks. So this is called a uniform distribution because for the most part, most of the data values are approximately about the same height. So the histogram can have 2 peaks, and in that case, it is said to be bimodal. And so going back to the picture we drew for the coffee, what can we say? Do we have 2 peaks or 1 peak? I would say that this is unimodal. So going back here, based on what we just learned, let's put it to use. The histogram of the data on the individual coffee consumption shows that shape-wise, it is unimodal. Another item to look for, or characteristic to look for, when you look at a histogram, is to check if it is symmetric or skewed. And how do you comment on that? Let us see different cases. You have a symmetric one, in which there's a line, an approximate line, through which if you cut through the histogram, one side will be a mirror reflection of the other side, approximately speaking. This is said to be symmetric or bell-shaped. In later classes, we're going to learn more about this type of distributions, also called normal distributions. But till then, let's focus on other types of shapes of the histograms. And that will be the left skewed distribution or the right skewed distribution. This is left skewed because it has a longer tail to the left. So this is left skewed or negatively skewed. And this is right skewed. Take note that it is the drawn out tail that determines the direction of the skewness. So, in this case, having learned these three possibilities, let's go back to our histogram on daily coffee consumption. Symmetrical or skewed. I would argue that for the most part, there is a line that can cut this into two approximately equal reflections of the other. So this is said to be symmetric. In statistics, there are no exact values. So in this case, the histogram actually shows that the distribution is symmetric or bell-shaped. Now we proceed to another important characteristic of histograms, and that is to inspect for the possibilities of potential outliers. In other words, we want to see if there are values that appear to stick out or separate away from the entire body of the distribution. You see, you should always point out any stragglers or observers that stand off away from the entire body of the distribution. Let's see an example of the histogram we have constructed on individual coffee consumption. And going back here, this appears to indicate that there is a single value here that seems to be standing away from the body of the whole entire distribution of possible values, and this might suggest the presence of outliers. So let's write that down. So there might be, in this case, potential outliers in the data set. Just to illustrate another example, if you're studying the personal wealth of Americans and Bill Gates is in your sample, he would certainly be an outlier because his wealth would be so obviously atypical that you want to point it out as a special feature. Now, when it comes to interpreting or communicating your insights from a histogram, what are things that are acceptable and what things are not acceptable? To illustrate, let's take the following example. The histogram shows the scores of 642 students on a psychology test. The test consisted of 197 items, each graded as correct or incorrect. Use the histogram to answer the following questions. Before we do that, just something to note. This is a histogram that reflects a summary for 642 students. The point we would like to stress here is that histograms are very useful. They tie very well with large data sets. In contrast, stem and leaf plots are very good for small data sets and depicting their distributions. Again, in particular, histograms for large data sets. So in this case, we would like to answer the first question. What was the lowest score on the exam? Please do not say 39.5. Whenever we have a histogram, there is no decisive way to tell what the lowest or the greatest score is. What we see mostly is just the distribution and where you have a concentration of the data values. That will help to answer the question of what is typical here. So, what was the lowest score on the exam? Unable to be determined from the histogram. So the correct question is unable to be determined from a histogram. Then question B, how many more students scored between 80 and 90 than scored between 70 and 80? That we can answer. Between 80 and 90, thereabouts, that was about 147. So these guys, you had 147 of them, and for between 70 and 80. So we have 70 and 80 somewhere here. That is about 107. The difference is 40. So there are 40 more students who scored between 80 and 90 than scored between 70 and 80. Then the next question is to describe the shape of the distribution. It appears that this tends to have a little bit more tail. Looking at this point, let's see, then this way. I would say that this appears to be slightly positively skewed or right skewed. So, slightly positively skewed. This can be a little bit subjective. Take note, this is same as right skewed. What that means is that more values appear to be greater than the most typical values than not. So having learned how to draw a histogram and how to extract information from a histogram, we now proceed to another type of graphical display for a quantitative variable, namely stem and leaf graphs, also called stem plots. And then alongside that, we'll consider a fashionably interesting one called dot plots, which are very similar to stem and leaf graphs. What is a stem and leaf graph? It's a simple graph that comes from the field of explanatory data analysis. It is a very good choice when the data sets are small in size. So, this is a quick example of a stem and leaf graph. If I were to interpret this, I will first look at my key. 4 bar 4 or 4 with the simple stroke there, the standing stroke 4 means the number 44, which means this stem and leaf plot represents the data set 44, 46, 47, 49, and so on. It appears the first number was kept stationary and the varying after number 4, 6, 7, and 9 made up the leaf. This is how we generate a stem and leaf plot. So we consider an example here. For Susan's spring pre-calculus class, scores for the first exam were recorded as follows. You have all the data values, and the following stem and leaf graph was created. Well, in this case, the stem and leaf graph has been created, so you have the number 33 based on this key. You have the number 42, there's 49, there's 49, 53, 55, 55, and so on. Take note that numbers can be repeated. So individual numbers are right here. Now, what I can see immediately that will help me to answer question 1, which says, where does most of the data fall? Is this. The leaf, I'm going to draw something like this, and you will be able to see this. And this is asking, where does most of the data fall? What I observed is that most of the data falls between this range, that is between 61 and 96. So I would answer between 61 and 96. Now, the next question says, if above a 90 is an A, what percentage of students earned an A? So, how many students scored above 90? That will be 2, this is this number, 1, this is 92, 94. I'm going to count them. 1, 2, 3, 4, 5, 6, 7, because this is 100. So this will represent 7 out of 31 of all of the numbers multiplied by 100%, and that is 22.58%. Then we are required to draw a dot plot of the data. So we need to go grab the data set and put it in StatCrunch, and it helps us to get the answer. So let's head over into StatCrunch, and I have the data set here, calculus exam scores. In order to plot the dot plot, I'm going to go to graph, go to dot plot, and grab calculus exam scores, and click on compute. And I'm going to zoom in on this, and I have the dot plots here. Then, after drawing the dot plot, if I'm required to also build the stem and leaf graph, which we just illustrated here, we can also do the same. Go to graph and go to stem and leaf graph. Indicate what variable you're working on, calculus exam scores from the title, and then click on compute. And here we go. We have the stem, and this is the leaf. So that brings us to the end of that part, and we're done with that question. So, with that said, we would like to consider the next example on page 24. And we begin here on page 24 with what an outlier is. This is usually critical whenever we are dealing with numerical variables. An observation of data that does not fit with the rest of the data, most times, is sometimes called an extreme value or an outlier. And so you see, when we drew a histogram earlier, we have most of the observations here, and you see a single value, which is a straggler or more or less an outlier or extreme value standing away from the entire body of the distribution. Then, just to reinforce our learning on stem and leaf plots, we are given the data here, which are distances from a home to local supermarkets, measured in kilometers, 1.1 as far as 12.3 for different individuals. So we would like to create a stem and leaf graph. The first step is to begin by setting up a key. I can see that there is a number before the decimal and a number after. I'm going to choose to represent 1.1, for example, as 1 bar 1. So which means a number like 3.7 will be represented as 3 bar 7. And a number like 12.3 will be represented as 3 and then 12. So to do that, you observe that I have the numbers that begin with 1s. So I'm going to write 1, that is fixed. This 1 is fixed. I only need to key in 1 and 5 in front. Then next, I'm going to note what numbers start with 2. And that will be those 3 I highlighted, 2.3, 2.5, and 2.7. So I'm going to write the fixed 2, then I'm going to enter in 3, 5, and 7. 3, 5, 7. Then next I have the numbers that start with 3, and that is 3 here. So you have 3.2, 3, 3, 5, 7. And then you have 4, you have 0, 2, 5, 5, 7, 8. Then for 5, you have 5 and 6 to represent these numbers. And then for 6, we have 5 and 7. Then there's a jump to 12. Take note of this. Very, very important. So I'm going to write this again. If we have a 12 here, we must sequentially and consecutively enter the numbers accordingly, like this. So there is no jump. We have to write all of these numbers. And this is one of the reasons why we say that stem and leaf plots are mostly effective for small data sets. So based on this, then I can do a little bit of drawing. And I have the last number here, which I should not forget to key in. And that is the number 3. And so you have 12.3 there. So with that said, those data values are given. Those data set values are given in a stem and leaf plot. And then we're ready to answer questions. Does the data seem to have a concentration of values? Yes. For the most part, between 2.3 and 4.8. Here's where you have the concentration of values. So between 2.3 and 4.8. 12.3 is a suspected outlier because it does not seem to fit with the rest of the data. And what is one drawback of a stem and leaf graph? Not very appropriate, not very appropriate for large data sets. Oh, yes.